Hello everyone and welcome to 24 Hours of Pass SQL Server 2014 edition. We're excited that you could join us today for Pedro Lopes' session on SQL Server 2014, Changes to Query Plans. This 24 Hours of Pass event consists of 24 consecutive live webinars. The recordings from all of these sessions will be available next week at www.24hoursofpass.com. My name is Vicki Van Dam, and I am a project manager at Pass HQ, and I will be your moderator today. I have a few quick intro slides before handing things over to Pedro. He's going to speak for about 45 to 50 minutes, and then we'll have a bit of time for Q&A at the end of the session. Next slide, please. Should you have any issues throughout the session, you can raise your hand using the hand icon on the right-hand side of your screen. To maximize your screen, use the Zoom button located at the top of the presentation window. There is also a question pane located on the right-hand side of your screen. Feel free to enter any questions there at any time. We will get to Q&A at the end of the session, and at that time I'll read your questions aloud to Pedro. We'll just have to see how much time we have and how many questions we have to get through. There is also going to be a short evaluation which will appear at the end of the session. Your feedback is very important to us and very important to our presenters, so please take a moment to complete the survey. Next slide, please. We would also like to take a moment to thank our event partner, Microsoft, who is one of our global sponsors. 24 Hours of Pass would not be possible without their support, and they are the reason that we get to provide this great free content to the Pass community. Next slide, please. I'd like to bring your attention to the upcoming Pass Summit taking place in Seattle, Washington from November 4th to 7th. The Pass Summit will feature over 190 sessions delivered by world-class SQL Server experts. The Pass Summit is planned and presented by the SQL Server community for the SQL Server community. This is the largest gathering of SQL Server and BI professionals worldwide. With over 5,000 attendees, the Pass Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. More importantly, Pass Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and the skills you need to stay ahead of the curve. You can contact one of the local chapters or even one of our virtual chapters for their discount code, which will get you about $150 off. And to optimize your savings, if you register before June 27th, you'll get in before the next price bump. If you want to find out any more information, just check it out at www.passsummit.com. Next slide, please. I'm now happy to introduce the speaker for this session, Pedro. Pedro is based out of Portugal and is a premier field engineer. He develops and delivers technical content focused on database engineering troubleshooting and TSQL query optimization. You can check out Pedro's blog, Sharing T-SQL Scripts in the SQL Swiss Army Knife series, by following the URL on the screen now. So without further ado, I give you Pedro Lopes.
Thank you, Vicki. So good morning, everyone. At least during my time zone, it's in the morning. Our agenda for the next 45 to 50 minutes will consist of these two topics. We will briefly talk about incremental statistics, so making statistics over large tables easily managed. And we'll also speak about the new Cardinality estimator changes, and our goals for those changes and how and when we should apply them. So some facts about statistics. As you can see on the screen right now, this is the classical definition in books online about statistics. So they do hold information that will allow the query optimizer to try to ascertain the cost of the inputs and try to come up with an optimized plan as much as it can. So the statistics are comprised of, at least as we can see those, are comprised of three parts, if you will. So we have a header, and amongst other data, we'll have the last up-to-date date and time. We have the row count, so the cardinality of the table. We have the samples on which, the number of rows on which the statistics were sampled. It could be full samples, so the row count will equal the row sampled, or it might be different. And it will show how many steps we have in a statistics blob. which can only have a maximum of 200 steps for now. Then we also have the density vector, which holds the statistical information, I would say, about correlation of values amongst all the columns in the statistic. So this will show essentially the number of distinct rows in the column values that are part of the statistic. And finally, we have the histogram. So the histogram will show the distribution of the values in the first column of the statistic. So it will essentially show you the ranges and the amount of rows per range and some other information. This is just a fact check. We also have a known recompilation threshold. So assuming that we have auto-update statistics turned on, we have a recompilation threshold which equals 20% of the table cardinality in changes plus 500. This threshold is a little bit different between permanent tables and temporary tables in the sense that temporary tables, when the cardinality is up to 6 rows, every 6 rows, so 100% changes, will trigger a recompilation of this. Then we also have the trace flag 2371, which changed. This was introduced a few versions ago. This changed the this fixed threshold to a sort of a dynamic percentage, and this is based on the formula roughly you see on the screen. So either the minimum value available either on the default recompilation threshold or the square root of the table cardinality times 1,000. So whichever is smallest will be used at the time to trigger statistics recompilation. So what were our challenges regarding statistics prior to SQL 2014? So one of the risks is that statistics will become stalled. So in SQL 2012 and below that, we would still be we could still have issues with large tables and the statistics that were created on those tables. So a recompilation threshold that was built on the entire table, when you would have multi-million rows or billion rows, would be almost impossible to reach. We have in an introduction of features, so to speak, that help on this, which were filter statistics. Those are an option to overcome, to partially overcome this limitation, but those have to be manually managed. So we still have an overhead in terms of work for any DBA. So another challenge was that we would either have to scan an entire table, or and that would be very resource heavy, of course, or we defer to sampling. Now the sampling, unless in a perfect world we would have evenly distributed values, sampling could be inaccurate and thus lead to inaccurate estimations, as you will see in the next part of our presentation. So this again was another challenge we have. And ascending keys. So this is I would say, a classical issue that could arise if we have a classically defined clustering key based on, let's say, an identity value. So if the key is as an ascending characteristic, so new insertions into that table would not be reflected by the statistics until an update was triggered. And I have a little asterisk there just to remind me that the new cardinality estimator also plays a very important part in handling the ascending key issue, and we will see more on that a bit later. Another challenge is that we would only have one statistics block for the entire table. So because we would have only one statistic with all the max 200 steps for possibly a very large table, we would have one single statistics blob, and that would also possibly make statistics upkeep might be difficult and could lead to inaccurate query plans. So this for our challenges. So then comes incremental statistics. So given all I've just spoke about, incremental statistics are targeted as partition tables. So this was our goal when we tackled this issue. So first of all, we are assuming that a sort of sliding window scenario exists. So most updates, as in an ascending key scenario, will be done on the newer partitions. This is, however, a feature that has to be explicitly turned on, as we will see a little bit later. The global recompilation threshold, so the global recompilation for a table statistic, when incremental statistics are turned on, have changed in this scenario. So have changed to 500 modifications plus 20% of the average partition size. So what do I mean by this? So instead of being the 20% of the table cardinality, it will be 20% of the cardinality on the non-empty partition. Okay? And this is used as the recompilation threshold for a global statistic. But statistics are maintained and created by partition. So the autoplate, so is triggered on a partition level, again using 20% of the partition cardinality plus 500 changes. So we still defer to the row modification counters to do this. So what happens when we add new partitions to a large table? So we must update statistics to include those new partitions in the entire statistics tree, which is something I'm going to speak about next. So we still use a global table blob, global table statistics blob for the query optimizer. So although I just said that we do upkeep statistics in a per partition, those are still binary merged into something we call a statistics tree, and that statistics tree will then be used by the query optimizer to do its job. So this is an example. Let's say we created a table that has 4 partitions. We have a statistic created per each of the partitions, but as you can see, those are merged into a statistics tree. So these are binary merged. And we persist the entire statistics tree, not necessarily each statistic by its own. Then let's say we add another partition, so a 5th partition. Then we have to update statistics. So as you can see on the screen right now, the 5th partition statistic is then merged onto the statistics tree, again, the statistics tree being the persisted blob that will be used by the query optimizer. Okay, and so adding a new feature means we have new syntax. So as you can see on the screen, either to create statistics or to update statistics, we have some new syntax available. We can update statistics on specific partitions now. As you can see in the 3rd place there, that's a way to turn on incremental statistics, which, like I said, are not enabled by default. And you have some other options, as you can see on the screen. So a few heads up, we don't support incremental statistics that are created for indexes that are non-partition aligned, which makes sense because, as I just said, we aimed this new feature at partition tables. So it makes sense that only partition aligned indexes will benefit from this. Always on readable secondary, so we cannot create an incremental statistic on a readable secondary database in the always-on deployment. On read-only databases, filtered indexes, as you can see, and also internal tables, for instance. So these are actually not, for the time being, this makes sense, being this support limitation. So let's do a quick demo on incremental stats, and I'll pull up my VM now. Okay, hope you can see it. So for this one, I'll create a new database called stats test, and I will turn on the incremental statistics on the database level. And let's check with using database properties if we do have those incremental statistics turned on. So as you can see, we do. We do have auto create statistics, and those are the incremental properties turned on. So now let's set up a table partitioning. As you can see here, a very simple partition function. I will be, as you might recognize from the values, I will be using 3 distinct dates. in my new table. So let me just create this. Okay, and now let's create a table that is actually quite simple. And we'll create a clustered index that will be part of the partition schema. And afterwards, we will then update. This is one form of turning on update statistics. In this case, in all the statistics of the stat table. Okay, and it's done. Let's just check if it is indeed turned on. It is. You can see here. So the incremental property is indeed turned on for the statistic that has this time. Good. Now I will insert some data. We will have to be quite fast, so I'll just insert 2,000 rows for each of the days between December 1st and December 3rd. And so let me insert this. Okay, good. Now let's check if we do have the partitions with data in them. We do. As you can see, the three partitions, we have three partitions here with 2,000 rows each. Do mind that we do have an empty partition, and I will refer back to this in a moment. So let's just update statistics with full scan, clear the proc cache, make sure that we start our demo with a clean slate. Good. Now let's check for the incremental property and the row partitions if everything is all right. So indeed this is the same. And as you can see here, so we have a statistic that was just updated, and we have 6,000 rows and 0 on the modification. So we're all set to go. Now, if we defer back to the slide I just talked about a few minutes ago on the recompilation threshold, for the full table to trigger an autoplate on the full table, we would need, so this is the classical representation, so 6,000, 20% of the 6,000 rows, the table cardinality, plus 500 modifications would mean that 1,700 modifications would be needed to trigger full table statistics update. But we have a partition table, we have incremental statistics, so this changes a bit. In this case, it changes to 20% of the average of non-empty partitions. So if you remember, we have 3 non-empty partitions. Each of them has 2,000 rows, so the average per partition is, of course, 2,000. Plus 500 modifications would mean that by updating 900 rows, we would trigger an autoplate statistic. Makes sense, right? So let's update this. We'll be updating 900 rows now. Here we are. So 900 rows were affected. And what did we get? So with this, we can check that we still have the 6,000 rows in the statistic, but we now have 900 on the modification count. Although we got to the threshold, the statistic was not yet updated because nothing has triggered it yet. So what I will do next is do a simple select count from that table, and so I will be running all of this. So we check the before status, so to speak, trigger the update, and see if everything got updated afterwards. Let's run this. And it did, as you can see. So the 900 modifications would make the statistic eligible for recompilation. And after we needed to touch that statistic, so recompilation happened, and we see that the modification counter was reset to 0. Okay. So let me just clean up this, and we'll move on. So going back to our slide deck, next we have the new cardinality estimator. So let me just start with a brief primer of the query optimizer. So what are we indeed talking about? So the query optimizer will take, essentially it will take a user's query and return a query plan. And within the query lifetime, so to speak, we can see that the query optimizer rests after an algebraic tree has been created, and before the execution plan is sent to the query executor. So what happens inside the optimizer? So in a nutshell, because this is not a query optimizer focus session. In a nutshell, we will be, or the query optimizer will use the knowledge it has on possible resource usage to drive its choices. And it has over 400 rules that can be applied to any given query, depending on the transact SQL that we input to the query optimizer. So a few changes that can be done are, for instance, the join reordering. So the joins have commutative properties that are part of the rules that the query optimizer can enforce. Expanding views, for instance. So although we have a hint not to expand views, the default behavior is to, when we query a view, the query optimizer will expand the view to the underlying tables and work from there. So while the semantics of the queries are being kept, the query tree, so to speak, can indeed change. So it's the estimates, so the estimates on the costs that are an input to the query optimizer will then drive its choices and make it output a specific result. So these are the cardinality estimates. So why do we estimate the cardinality? So the cost is based, as you can see, on the number of rows that each operation will return. And how do we know that? Well, the query optimizer only knows that based on the metadata it has, so on the distribution statistics. And we do have some cases where we don't have statistics, or we apply some, I would say, fixed estimates. A classical case would be when we use temporary table variables, sorry. And I do have in my blog a few other cases where we use fixed estimates to determine cardinality estimation. So the query optimization is with all this I've just explained, we can understand that this is a more or less unpredictable process in the sense that it is sensitive to the data it has or the metadata it has on the cardinality estimation. So this will influence the cost. The cost is normally an indicator of large or small response time. So we can correlate that by having poor estimations. This usually means that we have inefficient plans. Okay. So first and foremost, having updated statistics matters. It's not the only thing, but it does matter. So a few basic terms that we will be using in the next few slides, just for a quick reference. We have the density, we have the frequency, and we'll be talking about selectivity of a specific predicate. So that means the number of rows that will satisfy a specific predicate, as you can see. So the old or the classical cardinality estimator makes some assumptions to do its job. So the first assumption is uniformity. That means that we assume that distinct values within a specific table are evenly distributed, but they also have the same frequency of occurrence in the statistic, or in this case, the table. So more precisely, in each histogram step, we have this. So we assume that the distinct values in there are evenly spread, and we can see that in the histogram that the real world is not exactly like this, and each value would have the same frequency. So this is one of the assumptions we make in the cardinality estimator up until the SQL 2014. Another one is containment. So another assumption is that users will only query for data that exists. We also know that in the real world, this does not always happen. So, for instance, in an equijoin of two tables, what we do to estimate cardinality is to take each of the input histograms of each of the tables, apply the selectivity of the predicate inside to those histograms, and then merge those modified histograms before coming up with a joint selectivity. And we also have another assumption, which is independence. So we assumed that each column was independent of the other. So an example, we are given two predicates, predicate 1 and 2. They do not involve the same columns, so it's not a self-join. In this case, we estimate cardinality by multiplying the selectivity of the first predicate by the selectivity of the second predicate. But again, in the real world, we know that many times we query on columns that have some form of interdependence between them. Okay, so we have also tried to tackle with this assumption. So why would it change cardinality estimation? Well, first, we have the same cardinality estimation engine since SQL Server. That's right, a long time. Then throughout the years, we have implemented a number of changes to the query optimizer. Although you might be updating your SQL servers regularly, those changes are not actually implemented in the sense that they, since SQL 2005 Service Spec 2 CU6, I believe, were aggregated under trace flag 4199. So that means that any change we have implemented to the query optimizer, because it can lead, or we don't know if it can lead to a unforeseen result. We usually tell customers to, if you want to implement the changes that we have been putting out in our updates, you have to use trace flag 4199. Although, do test, of course, like anything else. Do test on your test environment and make sure that you don't have any unforeseen results. So the goal was simultaneously to enhance the quality of estimations. So we tackled a very broad range of workloads from OLTP, data warehouse, decision support systems. But also, we aimed to create better plans for most cases, especially those very large and complex queries. On our end, also, it serves a purpose to make not only performance smoother, more predictable, and fixing or changing cardinality, the cardinality estimator in the new cardinality estimator, it will be easier for us to maintain. But do keep in mind that the new cardinality estimator coexists, so it's side by side with the old cardinality estimator. So on a few borderline cases, if you test and you find that perhaps the old cardinality estimator does a good job for a specific case, or a borderline case, like I'm saying, we have an option to still force the usage of the old cardinality estimate. So what assumptions have we changed? The independence assumption becomes correlation. So we no longer assume that the columns are independent of each other, so the data in the column. These are usually correlated. So this is one of the assumptions that we changed in the new cardinality estimator. The second one is containment. While we use simple containment, so simple containment would be we would apply the selectivity of the predicates to the base histograms, and then we would merge the histograms to come up with joint selectivity. Now we have turned this into base containment. So we use a sort of probabilistic approach. This means that we take the base table histograms, we derive cardinality from there, and only afterwards do we factor in the selectivity of the predicate to then come up with a joint selectivity. So this assumes, of course, the containment is only done at the base table level. Okay? So how do we know, or how can we tell if we are using the old cardinality estimator or the new? So as you can see on the screen, one of the first things to check would be the compatibility level of the database. If using a compatibility level of 120 on SQL 2014, then we are using the new cardinality estimator by default. Otherwise, if we have any other compatibility level, then we will be using the old cardinality estimator. Okay, so this is one way of using this. Then we also have a trace flag, which can be either turned on the query level or on the server level. And this is also the hierarchy on which these are used. So if we use, let's say, a query that has the trace flag 2312 in the query, even though the database might be in SQL 2012 compatibility level, we will be forcing the new cardinality estimation on that specific query. So the precedence works like this. Some things we do have to watch out for, even in the new cardinality estimator, are statistics. So there is no change in the sense that we still use statistics, of course. This is the way we estimate our cardinalities. So make sure these are updated as much as possible. If possible, do make it a standard to have autoupdate and autoclear statistics turned on. Of course, we know there are exceptions. We know that there are cases that we do have to change the default. But I'm just saying, as a default, do try to keep this on because these are made to help you. Also, indexes. There is no amount of cleverness that we can put in the new cardinality estimator that will cope with not having a proper indexing strategy. So do capture your workload, analyze the query plans, look for the heavy operators, see what you can come up with, because indexes still matter a lot, of course. And independent of some things are independent of the cardinality estimator version. So the new cardinality estimator only targets changes in non-leaf level operators. So this means that we target joins, unions, group bys, and distincts. So all other operators are not influenced by the version of the cardinality estimator we are using. So things like local variables, table value functions, table value parameters still behave the same no matter the cardinality estimator version that you are using. So some common issues we try to address with this new cardinality estimator. So we aimed at making joins or the join cardinality estimations become consistent, even though this can be reordered. So even though they can be commutatively changed. And we have some heuristics that are used to in some borderline cases, to adjust this join estimate in a probabilistic approach, like I just said. And also we address ascending key. So ascending key issues, we always assume that the query values that will exist in the data set, and we will derive the cardinality estimation by using the average frequency, as you can see on the screen. So we have the same heuristics being applied here as we would have to missing values in any sample statistic. Do mind, however, that trace flags 2389 and 2390, which used to be one way of dealing with ascending key issues in your SQL servers, will no longer be relevant. So using the new cardinality estimator, you don't have the need to use these trace flags anymore. So let's see some things that are new about joins, for instance. Exponential backoff. Sorry, not about joins, about the cardinality estimator. Exponential backoff. So this is, let's take this example. This is a change in calculating the density of more than one predicate within a single table. Let's take this query you see on the screen. So we have a table cars, which have some cars, of course, in it. And in those, we have 200 entries that are Hondas. And from those 200 Hondas, 50 of them are Civics, the Civic model. So how can we derive cardinality from here? So in the old cardinality estimator that we, as I just said, we assumed that the predicates were independent. We would factor in the density of each of the predicates, then multiply by the table cardinality, and we would come up with an estimation. In this case, if you look at the query, if you look at the data, we know that we will have 50 rows coming out from this query, but the old cardinality estimator would estimate 10 would come out. So this could, at this very low numbers, might not significantly change the query plan, but it might do that. In the new cardinality estimator, we have something called exponential backoff. What is it? So again, we take the density of the predicates up until the first 4 predicates. If there are more than that, we don't account for the cardinality of those. So, and we, as you can see on the screen, we take the density of the first predicate, then we factor in the square root of the second predicate, and so on until we reach at most the 4th predicate. Then we multiply by the table cardinality, and in this case, it would come up with 22 rows as being the estimation, much closer to the actual rows we are retrieving. So the new cardinality estimator will take a more conservative approach. And in this case, as you can see, it's more correct to do so. Then the containment assumption we just spoke about. So take this query here, where we have a join between 2 tables. And besides the join argument, we have a couple of predicates that are applied to each of the tables. In this case, we have the the type, we filter by the type of the returns table and the date in the type in the sales table and the date in the returns table. To estimate this cardinality in the old selectivity, in the old cardinality estimator, the joint selectivity would be computed on modified histograms. Remember, I told you that we would take the histogram of each of the base tables that we were using. We would apply the selectivity of the predicates to those histograms, take those modified histograms, and then derive the cardinality estimation from those modified histograms. Well, and this is the formula that we more or less would be using. In the new cardinality estimator, however, we will take the base histograms. We will then apply the cardinality of each, or the selectivity, of each of the predicates that we are using, and then we come up with the selectivity or the estimations for the entire joint. Another joint change that we see here, so equijoints with multiple predicates. Okay, another example. So we have table 1 here, which has 12 distinct rows and it's on 12 distinct values and only 12 rows. And we have a table 2 that we are joining. You can see the join arguments in the center in the red box. And we have the table 2 that has 10 distinct values over 144 rows. So how do we derive estimations from here? So first we take the input that has the lesser amount of distinct values. So that would be the 10, as you can see in the color code. Then we would multiply by the average frequency for each of the inputs. So in this case, from table 1, we have 12 distinct values, 12 rows, and that means that the average frequency is 1. On the second table, table 2, the average frequency is 14.4. So this makes 144 rows. And this would be the result of our query. So 10 distinct values over 144 rows. So the new, the change we have made here, like I said in a few slides back, is by using now base containment in the new cardinality estimator, while we used simple containment in the old version. So this means that the selectivity has a better quality in this case. Another change is equijoints with a single predicate. So the new cardinality estimator now uses a simpler join estimate algorithm that will align the histogram using only the minimum and the maximum boundaries of each of the histograms. So in this example, we take a full 200-step histogram from table 1 and table 2, and then we will align the histograms using their min values and their max values in the entire histogram boundary into a single step. And we take that single step and we use that to derive cardinality. So as you can see, these will all be merged into a single step. So this is for equijoints with a single predicate. For non-equijoints, we apply more or less the same algorithm, although the histograms from the two inputs are joined using the non-equijoin operator instead of the equality operator, as you can see in this example. So when should you use a new cardinality estimator? First, if we are dealing with predictability issues. So widely varying query plans come out of the same query. Also, data warehouse workloads. Do test them, of course, but this can usually yield much better results. So always test your workloads, because like I referred earlier, there are some hedge cases that we might refer back to the old cardinality estimator, but generally this makes for a much smoother performance. And we also have a couple of extended events that will allow us to see on the new cardinality estimator, will allow us to see how the choices are being driven. So we can have more data to see how the changes are being made by the query optimizer. So let's do a brief demo on this. Let me again pull up my VM. And for this, we will be using the AdventureWorks DW 2012. I know we still use the same databases, but this is what we have, and I've built my demo around that. So first change I'm going to do is make the compatibility level SQL 12. So this would force the old cardinality estimator. So the first example I have here is about data correlation. So if we look at this example I'm going to show you, we will see that the currency key and the sales territory key in the fact internet sales table are strongly correlated with each other, as you can see. Now, let me just enable the. What we'll be doing first is to do a select of that table, fact internet table, where we have one predicate and the second predicate, as we have just seen, are closely related. So in the old cardinality estimator, we would assume these were independent, and we will be forcing the old cardinality estimator here. So let me just clear the cache. Okay. If you look at the execution plan, okay, we have a missing index warning there. But if you look here, you have the estimated number of rows being 770, while the actual number of rows is 6,700. So quite a large skew. And this is done because we are assuming that the predicates are independent. Let's explore this a little bit more. So what I will do here is to create an extended event session, and I will be using one of the new events I just spoke about. And we'll be outputting this to a specific file, and then we will look at that file. Let me just check if I do. Okay. This is from previous attempts. Let's delete them. And it's here. Good. So we're good to go. So let's create this session. And let's start the session to actually retrieve some data. And then you'll see how the new cardinality estimator changed the independence assumption to the exponential backup we just spoke about. So in this case, I'm going to run the query. We will check the plan and also stop the event session at the same time, and we will look at the data that we collected. Okay. So with the new, of course, we have our results here. We still have, of course, a missing index warning, but when you look at this index scan, we see that now the estimated rows are 2,200 for the actual row number, of course, of the same 6,700. So much closer to the actual result, which means that this has the real potential to, if we would have a proper indexing strategy, we might even get a better usage of or better query plan out of all this. Let's also check the event session we created, and let's see what kind of info we can retrieve from there. So we have the event here, and if you look at the calculator, this will tell us how the cardinality was calculated in this case. So we can see that indeed exponential backoff was used, and we can see the calculator name here and the selectivity that was derived from each of the predicates we have, so currency key and sales territory key. And we also have the stat ID that was used to derive this cardinality from. Now, we can also look at the input relation here, and the input relation will tell us more information about how the statistics were used. So we have here the kind of operators that were being used. We have identified the columns or the predicates in this case that correspond to the columns we were using. We have the constants that were used in this case as our predicates, and we have much detailed information here to actually support and know what the cardinality estimator is doing. We also have this operation here, which is this operator here, which show us the actual statistics that were used. So we have the object ID, and again, we have the same information in this case about the statistics ID that were used. So we could go in and look at the actual statistics using DBCT show statistics and see more insight, take more insight from the statistics themselves. And we have, of course, the cardinality estimator estimation that was derived for this query. Okay. So let me close this one. So in just as a second demo, the ascending key issue, like we discussed. So we will be using the fat currency rate for this one. let's just check what is the largest date key that we have on this table. For reference, if we look at the currency rate table here, we see that we have a clustered index on that supports the primary key, the clustering key, and we can see that currency key and date key are part of this index, and date key is the second column in the index, as we might see here. So that means that the histogram built on the statistic that supports this index is done, as you can see here, in this order. So that means that date key does not have a histogram, and the histogram is only on the currency key. So that's why we have some other auto-created statistics here. And in this case, I do know that this auto-statistic here is supporting as a histogram on the date key. So let's look at this. Let me just move this a bit. So let's look at this specific statistic here and check if what is the last step we have on the histogram. So if we move all the way down, we see in the last step that indeed the range high keys here is the 31st of August of 2008. And I have 12 rows that are in this range here. Good. So what we'll do now is insert, in this case, 10 other rows, which will have a date, or a key in this case, a date key that is larger than the max that exists right now, which is this one. So let's insert these 10 rows. Okay. Now, the histogram does not have this new data. So we can check again the histogram. And we can see that the last step is still the same 31st of August. So we are not reflecting this new input in the histogram yet. So let's look at how the old cardinality estimator would estimate this query. So of course we get the data, we should of course, but if you look at the execution plan, we did a clustered index scan, and if you look at the estimated number of rows, we have 1. While the actual number of rows is, of course, the 10 rows we have inserted. So this is on a very small scale, but consider that we might have, in this ascending key issue, thousands or tens of thousands rows being inserted. On a very large table, we would not be hitting the threshold that would trigger an update, and we might have some very inefficient plans coming from here. So moving back to our script, let's clear the cache and start our session again. Okay. Now let's, I will be doing this at once. So doing the same query, forcing the new cardinality estimator. This will be forcing the old cardinality estimator. Okay, so I'll be running both queries at the same time. And then I will stop our session so that we can see data that is in there. Okay, so of course we have the same output as we should. If we look at the execution plans, if we look at the first one, so this is the new cardinality estimator being used. So you can see that the estimated number of rows is 10, and the actual number of rows is of course 10. So we have dealt with our ascending key issue here. Of course, again, if we look at the old cardinality estimator, we see that there is a large skew because the estimated number of rows is 1 and the actual number of rows is 10 in this case. Okay? Do remember that this would be even more of an issue as more rows we would be inserting in this ascending key and would not be inside the histogram yet until we hit the update threshold. So let's look at the session we have collected, so this one, and check which kind of data we can get from there. So we are using this event here. Remember that the first one, we can see by the time code here, the first one was the new cardinality estimator. So let's see what calculator was used. So double click here, so we see that the first calculator that was used was is the column in the interval. So we are assuming a selectivity of -1. Of course, it doesn't exist. In this case, it means the calculator failed. Of course, it's an ascending key issue that we are facing. Okay, we have detected that it's an ascending key issue, and then we use another calculator that is specifically designed for this scenario. And we use the specific selectivity. So in here we can use, and we use the average frequency and the statistic that we are using to correlate with it. Now, if you look at the second event, we cannot see the calculator list because we are only outputting this information, of course, for the new cardinality estimate. Okay, and although we can still have some information, like as you can see here, the statistics ID from where cardinality was derived, and some relevant data that exists on both counts. Yeah, this is what I showed. So just to finish off, let me show you that this was indeed being done by the the new cardinality estimator, and we confirm that the stats will still not be shown in the histogram. So we look at the same statistic. If we go all the way down, we see that the histogram has not changed. So it's indeed a different way to deal with the ascending key issue that is being dealt with by the cardinality estimator, the new cardinality estimator, and not any change that we were enforcing on the statistics, in this case, like forcing an update or something. Okay. Good. So, questions. I'm open for questions right now. How are you doing on time, Vicky?
You've got a few minutes for questions. That's no problem at all. Let's take a look. We've had a few come in. So Tim's wondering, are there any scenarios where the new CE would actually be worse than the old CE? Are there any situations to be careful of or any disadvantages to using the new CE?
So let me answer you like this. For most cases that we have seen, I personally have not seen one case in any of the customers I usually am that had those issues with using new cardinality estimator. We do realize that there might be borderline cases, so that's why we say do test your workload as you would before migrating to a new version of any database engine, in this case SQL Server. Do see if you have some adverse effects in a specific borderline case. If you do, you can defer back by using the trace flags by deferring back to the old cardinality estimator. But in general, do test your workload with the new defaults implemented by SQL 2014. And in most cases, like I'm saying, in my own experience, I do see better results. But it's not something that is completely transparent that it will happen in all cases. That's why we've implemented it side by side. So you can still defer back to it if needed for a specific case.
Thanks, Pedro. Okay, we've got another question from Mine. He's wondering, he's referring back to where earlier in the presentation you had said that the new CE would bring better QPs for DW workloads. And he's wondering, what about, would you also recommend that for OLTP type?
Right. So if you can look at later in the recording, but we have implemented this we have tried to make it an implementation that would serve best all the typical workloads, be those decision support systems, DW, or even OLTP. And so in general, I do think that you will get better estimations, better results. Again, do test your workload.
And Pedro, what happens when we enable the trace flog to turn the new CE on? Does it flush the cache, or how will this impact ongoing complications?
So
sorry.
The enabling on the server level or on the query level. So in any case, we don't flush the cache because these are side by side. You may have a new plan because if you are using a trace flag, let's say on the query level, you are using an option that is, when we use, like in the example I just did, we have the same query with the same syntax, I would say, but we were using a different trace flag in each of the examples. So that yields different plans. So we have two distinct plans because these are two distinct queries actually. Does that answer your question?
Great, yeah, thank you. And Frankie is wondering if the old or the new CE is being used in Azure SQL Database or in any other version.
I really can't tell, but do shoot me an email, or you don't have my email. You have my Twitter handler, so shoot me a tweet with that, and I'll follow up for you that information.
Thanks, Pedro. And Paul is wondering if it's possible to make the demo scripts available from your presentation today.
Yeah, I can put them in my blog. So I will write a post about it, let's say during next week, and I'll have both the PDF of the slide deck, and I can have the script put there. No worries.
Great. Thanks, Pedro. All right, well, that wraps up the questions that we've got for you. Thanks very much for a great session. That was really great. And we've got another session lined up about to start in 3 minutes. That's open questions on SQL Server 2014, Microsoft Azure, and Big Data starting in 3 minutes. Thanks again, Pedro, and thanks everyone for attending today.
Thank you so much. And do fill out the surveys because we really care about them. Okay, thank you so much, everyone. Goodbye.